So thank you very much. My name is Avanzini. I'm going to present joint work with Gilles, Barthe, Benjamin Grégoire, Georg, Moser, and Gabriele, Vanoni. So in a nutshell, our work is about a logical framework for reasoning about imperative programs with procedures and with sampling primitives. So these sampling primitives then make the program evolve probabilistically rather than deterministically. So from a semantical perspective, they now return a distribution of output. And the kind of properties that we are interested in analyzing are so-called expectation-based properties, like mean values of the output distributions and stuff like this. When we were thinking about these ideas from the paper, we had two concrete application domains in mind. The first one is complexity analysis of randomized algorithms, and the other one is the verification of cryptographic procedures or cryptographic routines. Okay? Although I have to say it's more like a general purpose framework, not confined to these applications areas, but these were really our motivations. Since we really wanted to use these logics, we had two main design principles in mind. On the one hand, the logic should be usable and it should be expressive. So usable, I mean we want to apply this one on realistic programs, which requires, well, maybe not complete automation, but some computer aid. Compositionality is key, and also we would like sort of to reason via program abstractures. And the expressiveness just means that the framework should not stand in the way, and one way to guarantee this one is to have some form of completeness properties. Okay. Now, our solution consists of three key components. The first component, and the most central one, is an adaptation of classical Horry logics. Okay, so triples in this logic take a similar form to classical Horry logic, but there is one central difference, apart from the fact that the program C now can be a probabilistic program. Namely, your assertions or your pre and post conditions are now not predicates on your state space, but they are real valued functions. The nice thing about this logic is that we can derive, or we can retain actually a lot of the nice features of classical Horry logic when you think about its compositionality, but also the kind of completeness properties it satisfies. The second key component is the integration within this logic of probabilistic relational Horry logic, BRHL, introduced in this 2009 paper, I think a Poppel paper by Barthe and others. So this is a relational logic, so it allows you to compare programs, where the intuitive meaning now of such a judgment is that if you run the program C and D in P-related inputs, they are probabilistic, they will produce two output distributions, but these two output distributions can be coupled up in a way that this coupling satisfies the post-condition Q. And this is something that allows us, for instance, through the integration of such a relational logic within this expectation-based Horry logic, it allows us to carry out abstractions, or if you think about cryptographic reductions, if you want to analyze cryptographic procedures. And last but not least, we integrated the overall approach in an interactive proof assistant dubbed EasyCrypt. So if we look into this first central component, this Horry logic, as I mentioned before, your pre and your post, they are now functions into the reals, which of course then also necessitates a new interpretation of its semantics. And very informally, this semantics just now means that your pre, your f, if you evaluate it on an initial state, then it upper bounds the expectation of your post with respect to the output distribution of your program. Okay, to give you some intuition, you have a variable x, you add the outcome of a dice roll. If you are interested in the expected value of x after execution, then this will be bounded by x plus 3.5. Okay, so this way you can reason about upper bounds on expected values, but you can also reason about probabilities, for instance, just by measuring predicates. So this one says if you flip a fair coin and you assign the outcome to a variable x, the probability that x will be had after execution of this statement is 1/2. Through this bar operator, we can also reason as in classical Horry logic. So this triple here says that if you have a variable y that is initially had, you throw a coin, you assign it to x, then you will end up definitely in a state where x is either head or tail, or y is equal, and y will retain being head. So far so good. There is a final component that is also crucial, namely we allow logical or auxiliary variables, and this really turns these triples into some form of schema, because these logical variables are implicitly universally quantified. So this judgment here holds for any function h that takes a coin and returns a real number, for instance. And this is something that is very useful if you think about building a library of facts, because now you have these schemas that you can instantiate to the situation, but it's also important or critical, for instance, if you want to reason about procedures. And of course, this also needs to be sort of reflected in the semantics of statements. So I think maybe the most nicest aspect of the way how things are set up is that if you look at the rules, they just look like classical Horry logic. Okay? Of course, you need to sort of adapt the rule for assignment, because now you do sampling, but here you just do the most obvious thing. You have to a bit adapt the weakening rule, because now you're not speaking about predicates, but real valued functions, and effectively you have to turn implication into an inequality. But if you look at the remaining rules, they are identical to the rules that you know from classical Horry logic. If you have a conditional, you perform case analysis. Composition of commands you do compositionally. And if you look at the while loop, you have to find an invariant that is preserved by the loop body. And I think this is something that makes it very nice. And then if you look at the results, we have two main, let's say, meta-theoretical results. The most essential, most basic one is, of course, soundness. Whatever you can prove in this logic is correct. So soundness, derivability implies validity. But we have also the inverse direction, which is a completeness result, namely that every valid judgment can also be derived. And of course, this is sort of a relative completeness result, because it's relative to the deductive system that you use for reasoning about these side conditions that you get. Okay? But in this way, the logic is really not standing in the way. The inference rule themselves don't stand in the way of proving the property you're interested in. I don't have too much time, but I at least want to give you a bit of intuition how all of that one now is integrated within EasyCrypt. So here you see a simple procedure. It's performing a while loop. The while loop is increasing a counter, and it returns this counter, and what we measure is the result of this procedure. And we want to prove that the number of loop iterations given by this counter is on average bounded by 2n. If you look at the program, this is quite easy to see, but let's prove it in EasyCrypt. Okay, so how you start is in EasyCrypt, you open, so to say, a proof or a EHL judgment with such a eHorry instruction, where essentially you specify the triple that you want to validate in the syntax of EasyCrypt. And now this brings you into a proof mode that keeps track of the goals that you want to prove. This is our initial goal. And then you have a tactic language or tactics that allow you in an iterative fashion, usually in a bottom-up style, to apply the rules of EHL in order to iteratively build such a proof. Okay? I don't want to say too much, but there is a bit of automation going on, or there are things, let's start the other way around, there are things we cannot automate. For instance, when you have a while loop, you need to specify the invariant. But for instance, if you have a code snippet that doesn't contain a while rule, then EasyCrypt allows you to perform or to jump over this code snippet and do all the computations for you. Let's look at a bit of a more interesting example that highlights the usefulness of the integration of this relational logic. So maybe you know quicksort. Quickselect is a selection algorithm that is based on quicksort. A selection algorithm takes an array, it takes an index k, and it's supposed to return the kth smallest element within this array. And what you do is you just sort, and then you return in the sorted list the kth element, but you can be a bit more clever if you use, for instance, quicksort. You don't have to descend in the partitions it creates, but you just have to look further in the partition where this index is lying. But from a complexity perspective, it has the same limitations as quicksort. If you start from a sorted array, the worst case complexity in terms of the number of comparisons, for instance, that you perform is quadratic, but you can overcome this problem by picking a pivot at random when you are partitioning. And you can then do a pen and paper proof, for instance, by constructing such a recurrence, analyzing this recurrence, and then you realize, indeed, on average, the complexity of randomized quick select is linearly bounded. But this is not really what we want to do. What we want to do is really, we start from an implementation, and we want to have a guarantee that this implementation satisfies a certain property. But at the same time, we sort of want to follow the standard proof, right? So here you have the standard way how you would implement quick select in an imperative language. So what you need to start is you first need to say, what do I want to measure? What do I want to analyze? Here it's, for instance, the number of comparisons that we are doing. So we just introduce a cost counter and always increase in the code the cost counter whenever we do a comparison. And then we are interested in the expected value of this cost counter. And now you can apply EHL to reason about the program. And of course, the most important part is to come up with an invariant for this while loop. And you can take the invariant that you get from the previous proof, or from your pen and paper analysis. And then, of course, you have to verify that the loop body is preserving this invariant. So in particular, this also means that partitioning has to preserve this invariant. And this is a bit tedious like this. And the way to overcome this one is to just say, okay, let's ignore the details of the implementation and abstract it. Okay? And so you have two important properties of quick select that you need for the cost analysis. You need to know how much the cost boundary is increased, and you need to know how the pivot is aligned after partitioning. Okay? And this is reflected in this program, and you can easily analyze it with EHL. But now the question is, how do you transfer this analysis to your real QSelect algorithm? And the way how we justify this one is by integrating relational reasoning with a rule that uses PHL in order to connect two EHL properties. This is sort of the idea. And of course, there are some side conditions that, for instance, have to relate in a way the preconditions of these two statements and the postconditions of these two statements. So just on an example, in PHL, you can prove that when partition and its abstructure receive identical arguments, then also their outputs can be coupled in such a way that the way they increase the cost and the result remains identical. And so now I can take this analysis on the abstructure and transfer it to an analysis of the original code. And with that, once we have this triple here, it's really not difficult anymore to show or to deal with this while loop here. And if you look closely, this actually recovers the original pen and paper proof. I don't want to spend much work on this final case study. Skiplists, it's a probabilistic alternative to balanced trees that you use, for instance, to implement dictionaries. And through its probabilistic aspects, it's sort of self-balancing and gives you good average case complexity properties. And actually, this was our driving example because it's really difficult to formalize. And actually, this was the example that guided us and that brought us to come up with the solution, how we have it now in the paper. And I think I will stop here. There's, of course, a lot of things that I did not present. So, for instance, as the title suggests, we also are interested in cryptographic games. So, for instance, in the paper, we present an adversary rule that allows you to reason about adversarial code, like which is needed if you do the kind of game-based cryptographic proofs. And for instance, Barbosa and others in a recent paper have used EHL to get a much simpler proof of security for the dilithium post-quantum cryptographic scheme. So this is also sort of an indication that our method is useful. In the paper here, in this talk, I've shown you just a simple excerpt of our calculus. In the paper, we define the calculus for the full core language of EasyCrypt with procedures and scope variables, which requires some adaptations. We have a frame rule to simplify reasoning and many more details. Thank you.
The preparation, and then let me just ask you one quick question. So we have this PRHL here. So and I just have a relational version for the EHL.
Oh yes, we have.
You do have it, isn't it?
Yes.
Cool.
So this is something that we submitted to POPL 2025.
I see. Okay, maybe we can discuss offline. Okay, nice. Thanks, Martin, again for the wonderful talk.